Okay, yes, we are live. Hello. Yes, we are going to go through the lecture series for the final chapter in your chemistry syllabus, which we call it the Introduction to the Chemistry of Transition Elements. And there's a lot of concepts that you're going to revisit throughout this chapter, plus a lot of new ones as well. All right, so get ready for a fun ride here. Now, if you look closely at the items or things around you, you may be able to spot some items or things that has transition elements made up inside, comprised of certain alloys that involve transition elements. Okay, today I'd like to highlight the coins that has been in circulation for many years. Okay, particularly the third series coins that has started circulating since 2013, and that actually features our national landmarks and icons. If you were to cut the $1 coin and look at the cross section, you'll be able to see a steel core that has been electroplated with many layers of metals such as nickel, copper, brass, and nickel again, where the design were embossed on it. And these are the associated elements involved in each layer of the metals. And you can just do a quick count. There's already about, there's 4 different transition elements just in a $1 coin. Now, particular special features for transition elements are their ability to form very beautiful colored complexes and compounds due to their ions that can be formed. Okay, so in a very interesting infographics from Compound Interest in 2016, it showcases some of the gemstones that is widely available in the world and how the colors arises, right? So if you were to go and pause this video and look at this section, right? Okay, they tell you the elements that are responsible for the colors. For example, ruby will be chromiums, replacing some of the aluminum ions in the structure. Okay, so aluminum oxide is the base structure for ruby, but because of the presence of chromium, it causes ruby to turn into red. Okay, we have sapphire here as well. Sapphire is due to titanium and iron ions. Okay, yeah. Another one that I'd like to show you is sapphires, right? Do look like blue, right? However, okay, you can have some kind of like contamination from other transition ions, transition element ions that actually cause a wide variety of colors, not just blue. Sapphires can actually come in these colors as well. So that makes the world a lot more beautiful. Yeah, and rubies are generally red, okay, because due to the presence of chromium replacing some of the aluminum ions in the structure here. And to reinforce the fact that us human beings are so obsessed with colored shiny gems, okay, you can see that we have like various different colors in Minecraft. We have so many different types of games that involve gems, like Bejeweled and so on. Then we have like using gems as our currencies. Like for example, this one from Genshin Impact. Yeah. So the world is really obsessed about gems. Now, we will come back to our syllabus and what we are supposed to learn from this chapter. This lecture actually will focus more on the physical properties from the first set of transition elements from titanium to copper. So you can actually see this from our first page of the notes. And I'll go through, okay, this part about what are transition elements, okay, and then how do we see the electronic configurations. We will try to link back to atomic radii and first IE, so get ready for that. And then how to contrast qualitatively the melting points and density to those of a S block element. So we are going to look at calcium as its closest neighbor. All right, so I've got the periodic table now behind me. So where do you think the transition elements are? All right, to look at them, you need to look at the D block elements, which is this middle part from group 3 to group 12. Okay, and take note that not all D block elements are transition elements. So there's a very specific definition to identify what are those elements. Okay, so our focus for our syllabus is on the first row D block elements, and we are just looking at these 8 elements. Yeah. Okay, so scandium and zinc is out of the definition, so that's why they are excluded. Okay, even though all 10 of them are your D block elements, okay, the middle 8 will be your transition elements. Okay, I'm going to digress a little bit to showcase the 5D orbitals that you need to know how to recognize, how to label, and how to draw. Okay, for the D block elements. Okay, and those are your dxy, sorry, dyz, dxz, and dxy, followed by dx square minus y square and dz square. Right, this will come into full effect in a later chapter or lecture, sorry, when we are talking about how colors arises. So do take note that this is going to become very important later on. Right, so for now, just take note of this. Writing electronic configurations, and we are looking at D block elements, and how do we look at the process of filling the D orbitals progressively. And remember this kind of diagrams, okay, if you have no recollection, it's somewhere in your atomic structure notes last year, whereby we were talking about the Aufbau principle, whereby you fill up the electrons from the lowest energy subshell first and progress upwards. Now the lowest one, of course, is 1s, and then as you remember, there is a sequence of filling up the orbitals. So 1s, 2s, 2p, 3s, 3p, and if you remember, 3d is not the next one. 4s is the next one. Okay, so here we have a reason why the 4s subshell is actually filled first before the 3d. So if you look at the relative energy levels, okay, the empty 3D subshell is at a slightly higher energy level than the 4s subshell. So your filling out of the 4s orbital has to take place before 3D. Hund's rule. Still remember this from atomic structure? Yeah, this refers to how you're going to fill up your electrons in the orbital of a subshell. So if you are looking at a 3D subshell, you are going to occupy each of the orbitals singly first with one electron before you doubly occupy them. And all the electrons you're filling in the singly occupied orbital have to be of the same spin, right? So we have an example of manganese and iron. Manganese has 3d5 for S2, whereas iron is 3d6 for S2, right? As you can see, this is the reason why or how Hund's rule has been applied. Okay, and just to recall what is the meaning of the square bracket AR, this means you are applying the electronic configuration of argon before this. Alright, so it's supposed to be 1s2, 1s2, 2s2, 2p6, 3s2, 3p6 here. Yes, I got a slide to reinforce that part just now. So by convention, in the question, it can showcase transition elements electronic configuration in this manner with a square bracket AR 3DX for SY. So you need to know that the square bracket AR is this configuration that precedes or that's before this part. Sometimes they can also go for a schematic box diagram in this manner, right? So their focus is more on the 3D and 4S subshells. Now, the issue is, can you use this yourself as part of your own answer? Answer is no. I'm sorry. I don't ever see students being able to write this one, okay, as a shortcut. You will have to go through the entire configuration yourself. Okay. If you are going to write it as an answer, I repeat, you have to write the full configuration. All right, now look at the second half of page 4 of your lecture notes. You'll see that whole range of electronic configurations for your first row D block elements, scandium to zinc. Okay. So this is actually going in sequence. So we start off with 3D14S2 for scandium, titanium is 3D2, vanadium 3D3, then there is an anomaly here for chromium. It's supposed to be 3D4 for S2, but yet it turns out to be 3D5 for S1. Okay. The sequence continues until copper, where it's supposed to be 3D9, okay, and no, it's not. Okay, it is 3D10 for S1. Okay, zinc continues the pattern. Right, so the two anomalies here, chromium and copper. So why so? So if you recall from your atomic structure lecture notes, okay, there's something about the extra stability from a half-filled and fully filled D subshell that gives greater stability to the configuration, right? So do look out for that link. Okay, we are linking back to a atomic structure from here. Hey, I'm back. All right, now we are at the forming of ions for transition elements. And if you recall, okay, when we are forming ions, we got to look at the ground electronic configurations of the elements and slowly remove the electrons on the outermost quantum shell first, or outermost subshell in this case. So for transition elements, we will form the ions by losing 4s electrons first, followed by the 3d electrons. All right, I still hope you all remember from that from your atomic structure lectures. So we are going to use manganese as an example here. So manganese ground state, okay, element is 3d54s2, and for 2 plus, right, okay, you will remove 2 electrons from the 4s subshell, right? So give rise to 3d5 alone, yeah, by at this point. Okay, and then manganese 3 plus will be removing the third electron here from the 3d orbital, okay, and hence leaving it as 3d4. Now I'd like to go through the reason why the 4s electrons are removed before the 3d electrons. Last time when we were doing the tutorial for atomic structure, many of you have the query about why it is so. So this is the official explanation how come it is different from your Aufbau principle. Okay, let's recap what's Aufbau principle is that you fill in your 4s electron first before 3d, right? Okay, and yet here the 4s electron is being removed. Okay, so why so? So the official reason is because when you occupy your 3d orbitals, right? Okay, it's occupied later than the 4s. But once it is occupied, okay, the orbitals will repel or shoo the 4s electrons away from the nucleus to a higher energy level. Meaning, okay, at the start when you are filling it up with electrons, okay, your 4s orbital empty is at a lower energy level than your 3D. So you fill out your electrons here first before 3D. Okay, by the way, when we are looking at this point, everything is empty. Yeah? So we are trying to fill out the electrons from the lower energy first. But once it has been filled up with electrons, your 4s orbital field now will occupy a higher energy level than your 3D. Okay, your 3D when it's being filled, okay, will stay around this level. So that's the interesting bit because of the repulsion. So hence, you are going to remove your outermost electron from the 4s first when you are creating the ions. Let's consider the loss of one electron at a time from your typical transition elements. So what are the possible stable electronic configurations that can result from it? Okay, and you can see there are actually 3 possible types. So if you were to use cobalt, okay, as an example, with a ground configuration of 3d7 4s2, okay, over here. Now, you can expect stable electronic configurations or arrangements from losing all your 3d and 4s electrons. That means all 9 electrons from here. So allowing it to achieve a noble gas configuration. However, it is a bit too highly charged. Right? If you remove 9 electrons, it becomes 9 plus. Okay, and that is not really one of the favored situation. Okay, too high charge density, by the way. Right, another way is just removing your 4s electrons. So you leave the 3d electrons untouched. So that will be your cobalt 2 plus. Yeah, and that's one of the common ions for cobalt. Okay, and a variety of or a range of 3d electrons being removed on top of your 4s. So you can remove any number from these 7 here, right? So your 3d subshell as a result has a chance to be partially filled. So it could be like 3d6. Okay, so if you remove 2 electrons from here and one more electron from 3d7, you will get cobalt 3 plus, which is another pretty common cobalt ion. So these are the 3 possible scenarios where you can remove electrons from TE, transition elements. Yes, we have arrived at one of the most important definition for this chapter, which is how to define a transition element in general. So it is a d-block element which forms at least one stable ion with a partially filled d subshell. So if you are looking at a first block d block element, right? Okay, this will be a 3D block element with partially filled 3D subshell, right? But we are opening up the definition to a more generic category. Okay, so we just use D block without the number, the principal quantum number, as well as here without the principal quantum number. Now in your D block elements, not all members can be treated as transition elements. All right, so we need to figure out which ones can fit the definition earlier on. Now, scandium and zinc are quite special because when they form ions, these are the only ions that can be formed for scandium and zinc as respectively, right? For scandium, it can only form Sc3 plus. There's no Sc2 plus or 1 plus, right? And for Sc3 plus, it's a stable ion with a empty d subshell. And for zinc 2 plus, okay, it's formed by removing the 2 electrons from 4s, leaving it as 3d10. And you don't have zinc 3 plus at all. Okay, this is the most stable form and it's the only ion form. So hence, because of this phenomenon, right, we will not treat zinc and scandium as transition elements. Now, there are also transition elements that do not show typical properties in certain oxidation states. And one of the classic ones again will be your copper plus and copper 2 plus. Right, copper plus is formed by removing one electron from the 4s1. Okay, do take note, this is the anomaly. Yeah. And for copper 2 plus, you take away one electron from 4s and one electron from 3d10. Okay, and for copper plus, because of its fully filled 3D subshell, okay, copper plus does not actually show typical properties of transition elements. Okay, but copper 2 plus can, because this is seen as a stable ion with a partially filled D subshell. Right, so it fits that definition. All right, we are done with the so-called the introduction part. Okay, let's go on to the more juicy part about the physical properties of transition elements. And you can see that we are trying to compare against the main block elements. Okay, typically calcium, by the way, because it's the closest main block element to the first row. Okay, for your D block. Okay, so let's go into the deep dive on the hows and whys. Now look at the table 1 on page 7, where it showcases the summary of the physical properties of the elements here. So the blue ones are your transition elements, and we have included calcium, zinc, and scandium here as direct comparison. Okay, so zinc and scandium are in the same D block. Okay, and calcium is the closest main block element for comparison. Okay, so in general, transition elements are hard and have high densities, as you can see from here, as compared to usually we'll compare to 1.55 calcium's one, okay, and have relatively higher melting and boiling points. So yeah, calcium has less than 1000 melting point, less than 1005, and titanium to copper, okay, yeah, in the thousands here, and yeah, 2000s and above for boiling point. Okay, I'm just looking at the data here as a rough comparison. So you don't have to really like do a detailed comparison for physical property values. Okay, do take note of that. Now for atomic radii, okay, if you look at this row of elements, sodium to chlorine, you should be able to identify them as your period 3 elements by now, right? And if you look closely at the atomic radius between the first element, group 1, sodium, and chlorine is in group 17, you realize that there's a very big difference in their atomic radius. So if you compare from the leftmost to the rightmost element, okay, the difference is 0.087 nanometer. How about the first row D block elements? Okay, now just looking at the middle 8, titanium to copper, you realize the difference in their atomic radii is just 0.015 nanometer. 0.015 nanometer. That's really small as compared to the main period 3 elements. So unlike your elements in period 3, okay, we will say that the d block element shows very little variation in the atomic radii. So this is the idea behind this. Variation, because you can see it's not a direct decreasing trend. Yeah, this is it's like almost the same value for certain elements consecutively, right? So we just have a rough idea that between the leftmost and rightmost of the identified row, okay, it showcases a very small difference here, right? Now in this slide, I'm going to showcase it in a graph. So in graphical form, okay, it looks very interesting. This part, okay, where the titanium and copper row was identified just now, okay, and particularly this part, you realize that from titanium to copper, there's a max difference of 0.015 nanometer, whereas just vanadium, okay, using vanadium as the leftmost, just one element away from titanium, the difference is only 0.005 nanometer. That's like relatively constant, more or less. Right, so there's something quite interesting about the trend of atomic radii for this part. Now, there's a particular description about this part. Okay, so why are the atomic radii of your transition elements relatively invariant? Okay, so the main reason is because, okay, as you're filling up your scandium to zinc, okay, do take note that your 4s substrate has been filled up beforehand. So now you're just filling up from 3D1 to 3D10. And this time round, your electrons are being added to the inner 3D subshell. Okay, this belongs to the third quantum shell, and 4s belongs to the fourth quantum shell. So of course, this is the inner quantum shell here. Okay, so as you're filling up more and more electrons to the 3D subshell, okay, you see that it starts to shield the outer 4s electrons more and more from the increasing nuclear charge. Okay, do take note, every time you go from scandium to titanium to vanadium, right? You're adding one electron and one proton also. Okay, so your nuclear charge is increasing because of the additional proton added, but yet your shielding effect is also increasing because you are adding more and more to the more and more electrons to the inner 3D subshell. So increasing nuclear charge from here will decrease atomic radius, and increasing more electrons to the inner subshell will increase shielding effect. Remember, when your shielding effect increases, radius will increase, right? Whereas this one, the radius will decrease. Okay, so as a result, okay, the increase in effective nuclear charge becomes very gradual or negligible, and hence the atomic radius remains almost constant in this segment. Next, we'll look at the melting points and boiling point data. Right. So for your D block elements, right, except for zinc, they all have very high melting and boiling points as compared to calcium. And the graph showing the trend of boiling and melting points actually shows a very interesting shape. I call this the M shape. Okay, yeah, it looks like a McDonald's sign. So what accounts for the very high melting and boiling points of your D block elements? Okay, we will compare that to calcium. Right, and the main reason is due to the stronger metallic bonds for transition elements. And in order to understand how this works, we need to recall what constitutes a metallic bond. So if you look at the giant metallic structure, okay, metallic bonds are formed between the sea of delocalized valence electrons, denoted by these red dots, and the array of positively charged metal cations, right? So you can't draw any lines here, okay, it's omnidirectional for metallic bonds. Now for the block elements, something interesting to take note is about the energy difference between your 4s and 3d electrons. In fact, the difference is so small, so we call it as 4s and 3d electrons are very close in energy. So even though the 4s electrons are the outermost valence electrons, right? Okay, the 3d electrons can actually introduce or be introduced and contribute to the sea of delocalized valence electrons. So now you have a lot of electrons in that sea. Yeah. And the metal ions can therefore also form cations of higher charge. Okay, so if you use two from 4s and one or two from 3d, technically you can form 3 plus 4 plus metal cations. Yeah, which is a interesting feature here. Okay, and on top of that, okay, the radius for your transition metal ions or cations are way smaller or smaller. Okay, I won't call it way smaller than your typical cations of your s plus elements. And the reasons are due to your higher nuclear charge, okay, for your transition metal cations and poorer shielding effect by the remaining 3D electrons. Okay, remember your 3D orbitals are kind of like a four lobes, kind of like flower shape. Okay, when those orbitals are filled up, actually the shielding ability is not as good as a p orbital or s orbital. Okay, so that's why the word poor is here. Now, what does it mean by poor shielding effect by the 3D orbitals? All right, in order to let's like do a visualization, a rough one, okay, on how shielding effect works for various types of orbitals. Okay, you can actually do a Google search like this. Okay, and it will be useful to visualize the shapes of the orbitals, which is like above me right now. Okay, this part. Okay, so in terms of your Google search, right, you will most likely get this if you were to search shielding effect differences between the various types of orbitals. So I just put SP and D orbitals here, right? So you can see that based on the search, you can there's this phrase that is highlighted there. Okay, then the s orbitals provide the most effective shielding, followed by p, and then lastly by d, right? And you got to see from the point of the spatial distribution and penetration of the electrons, right? So for s orbitals, this is what you have learned. Okay, a bit small here. Okay, but you can actually refer to the s orbital diagram in your atomic structure notes. Okay, so these are spherical and has the highest electron density near the nucleus. So as a result, right, it's able to due to its closeness to the nucleus, right, it's able to help to shield the outermost electrons from the full extent of the nuclear charge. So as an orbital has a great best shielding effects here or shielding extent here. Okay, for p orbitals, right, we learn it as dumbbell. Okay, and you'll be able to find various like diagrams of p orbitals on the net. Okay, how they look like. Okay, but the more I prefer this version here, a bit small again, but it's not really like a figure of eight. Okay, it's slightly larger in terms of its slopes, right? So because right, the electron density is more distributed towards the like the outer perimeter of the p orbital, so it is effective in shielding better than d orbitals, okay, but not as good as the s orbital, okay, because they are like not so close to the nucleus, right? So you will need to see this one combined in like the three p orbitals combined into one, okay, in order to see that is like the coverage, okay, or we call this the spatial distribution is better than the d orbital. Okay, and then for the d orbitals, right, okay, the main idea why even though they have like five of them with like four lobes each for four of them, right, and then when you merge them into one, which I will have a diagram later on to show you how it looks like. Okay, in fact it is not so good in terms of shielding effect as compared to the p orbital. It's because of the the diffusion of the uh, um, orbitals itself, right? So d orbitals are more diffuse, more complicated or more complex shape with multiple lobes. So essentially not able to be, the d orbitals are not able to be close, as close to the nucleus as your p electrons and s electrons, and therefore will not be able to provide a more effective shielding than p and s. I technically am just reading off this as you can see. Okay, in fact, is the reason why I chose to use the Google AI is because it's actually quite hard to find a article that consolidate this quite well. So you have to take pieces of explanation here and there in order to see the full picture. Okay, I'll try to attempt this again when I have a diagram on the d orbitals, all five of them all merge into one. Okay, later on. Density, pretty straightforward thing. Okay, D block elements are generally denser than the S block elements due to smaller atoms and more tightly packed structure, right? Due to the strong metallic bonds. All right, we have a graph plotting density versus the elements from calcium to zinc, and you can see that there's a general rise. Okay, and then the highest at cobalt to copper. All right, so using the formula for density, which is relative atomic mass over atomic radius, we can use this to explain that trend. Okay, and it's because there's a decrease. Sorry, my bad. Decrease in atomic radii across scandium to copper, while your relative atomic masses increase. Okay, so the numerator increases while the denominator decreases. So overall density goes up here, right? So that accounts for the general increase in the trend for densities. Okay, it's time to do a A-level question. Okay, it's a MCQ. You can pause the video here to do the question and then just restart. All right, now I'm going to explain or just go through the answer to this. This is a pretty straightforward question. Okay, so for which property is the data under the correct element? Okay, so we have copper and calcium to compare, and which one fits it correctly, right? And if you look closely, this seems to be the answer, which is the answer, right? Copper has a much higher density than calcium. Now for electrical conductivity, copper is a much better electrical conductor, okay, than calcium. So this one should be a higher one. So B is not the answer. Melting point, copper has a much higher melting point than calcium. So this value is wrong. It's supposed to be way higher than this. Okay, and for atomic radius, you had also recently learned that copper has a smaller atomic radius than calcium. So all these are wrong. Now we are at the trend for IEs now. Okay, ionization energies, which in this table we have the first IE all the way to the fourth IE. Okay, let's concentrate on the first two IE from titanium to copper and just take note of the trend. Just looking at the trend, and you'll notice something. If you were to plot the graph, okay, using the IE values from the slide before, you'll notice a very interesting shape for the first two IEs here. A little bit weird, right? Okay, notice the very small variations in the first and second IE graphs as compared to the third and fourth IE. This is the graph for plotting first IE across the very first element all the way until, yeah, I don't know how many. I mean, it's strontium. Okay, I mean, it's just plotted consecutively. Okay, now based on your previous IE graph, for your periodic table as well as your atomic structure, okay, you technically only learn here, yeah, this part, and then you learn group period 2 here, okay. Now you are now looking rightwards onwards to see how the transition elements first IE data falls into place, and you realize a very interesting bit here. Very small variation in the first IE. Why so? Okay, we need to revisit this the diagram that I mentioned. I'll be sharing you on how the 3D orbitals, as in the five 3D orbitals, okay, technically when you put them together, they'll form the subshell, right? So this is how it looks like when you combine them all into one compilation here. Okay, all right. So do take note that the nucleus is right in the middle here, all right? And when you go from when you go from titanium to copper, you are adding one electron per element. So you are increasing the nuclear charge. Okay, and at the same time, as you go from titanium onwards, vanadium, chromium onwards, right? You are adding one more electron to the 3D subshell. Now to supplement what I've said, you can see that if you were to use the periodic table and look at this row, okay, if you go from left to right, okay, the numbers that is circled in red is your proton number. So nuclear charge is increasing across this row. Okay, and at the same time, if you can see, the way the electronic configuration is changing is that your d orbital has one more electron than the previous one. Okay, and of course this one is an anomaly, right? This one and copper is the anomaly, but overall there's always at least one 4s electron here. So if you were to do IE, you're going to remove your 4s electron from here. Okay, your outermost electron from here, right? And you can see that even though your nuclear charge is increasing, your shielding effect is relatively increased also, right? Because you're adding your electron to your 3D subshell. So now we can answer the variation across the transition elements for the first and second IE. So it is seen as a small variation. Okay, so why so? Okay, so for your first and second IE, you are aiming to remove the 4s electrons. And do recall that in order to see IE, you need to look at these factors here, including nuclear charge, shielding effect, and effective nuclear charge, right? So nuclear charge, I tried to explain in the previous slide. Okay, so nuclear charge overall is increasing, okay, as you go rightwards in the row. And also, okay, you are looking at your 3D electrons here, okay? And because your 3D electrons are inner shells electron, they will shield the 4s electrons, okay, from the increasing nuclear charge. And because you are adding more and more 3D electrons, okay, this will lead to a insignificant increase in effective nuclear charge, right? Or you can call it minimal increase in effective nuclear charge across the transition elements. So as a result, because the increase in effective nuclear charge is so insignificant or relatively invariant, okay, that causes the variation to become relatively invariant or small. All right, and with that, we have arrived at the end of the physical properties for transition elements. Okay, and if you want to find out more about how they look like for example, how does manganese look like? How is titanium like? Some of us may not have seen cobalt in real life, for example. Okay, do check out this website called periodicvideos.com, or they have a very famous what's this YouTube channel, yeah. Okay, called periodic videos where there's a main character who is a professor at University of Nottingham, and he got his knighthood, okay, because of this channel, yeah, and his impact or contribution to the chemistry world. Okay, so if you're curious to find out how TE looks like and even like the other elements, they have a playlist of all the elements, one video per element, okay, yeah, in that channel. So do check it out when you have time. Yep. Now I would like to move on to chemical properties of transition elements, and why do such elements and compounds can exhibit notable chemical properties. And you have actually learned a little bit of this and like in past chapters uh, like kinetics when you learn about homogeneous and heterogeneous catalysis. How come transition elements are good catalysts? Right? So we're going to answer those questions here. And this is actually one of the areas where new concepts will be learned here. Yeah, here. And we are going to see quite a lot of like questions from the A level papers that ask from this segment. So do look out for new concepts like I would say a relatively new learning curve. Okay, when you start learning about colors and so on. Right. So let's see what's in store for us. This is the list of the learning outcomes for the chemical properties of TE. And you can see that we have like described the tendency to have variable oxidation states, oxidation state prediction, blah blah blah, and so on. And you realize E naught is here. So which means the previous two chapters that you learned before this are going to be used again. So get ready. And then this is from your kinetics notes. Okay, you definitely have learned this before. So if you forgot, you will have to go back to that lecture notes from J1, right? And then start trying to draw a link to that. Okay, what I want to emphasize is bullet point number one, this one. A lot of the reasonings here is because of this variable oxidation states of transition elements. So do watch out on how this reasoning can help explain the following phenomenon. Now, when we discuss chemical properties of transition elements, we will have four characteristic properties to look at. Number one will be your variable oxidation states. Two will be your catalytic properties. Three is formation of complexes. And four will be your formation of colored compounds and ions. Right? And for the remainder of this lecture video, okay, we'll be focusing on variable oxidation states. So you will see catalytic properties in the next video. Now, the very first chemical properties that we have to learn will be about the variable oxidation states feature. And the reason why your transition elements can exhibit various oxidation states is due to the close similarity in the energy, okay, of its 3d and 4s electrons. So it enables electrons to be removed from either subshell. And this feature was mentioned earlier on. Okay, if you remember that in the physical properties, we talk about boiling and melting points. And the reason for that is because of the greater metallic bonding, okay, or higher strength of metallic bonds. And it's because of this as well. Yeah, this factor, okay, that you can actually use electrons from the 3d and 4s due to the closeness in energy, right? So we are seeing the same feature here to exhibit variable oxidation states. So let's use iron as an example here. Okay, so iron, the ground configuration will be 3d6 4s2. Okay, and for you to form iron 2 plus, just take away 2 electrons from the outermost subshell or shell. In this case, it will be your 4s. So 2 remove, okay, you get 3d6. Okay, for Fe3 plus, take one more away from the 3d subshell to get 3d5, and it happens to be a half filled 3d subshell. Okay, now if you were to compare to s block, okay, s block meaning your outermost electron is in an s subshell. Okay, like 2s something, 3s something, sodium, potassium, and so on. Okay, those are your s block elements, calcium, and so on. Okay, so once your s electrons are being removed, there's no way to remove any more electrons from the inner shell p uh, subshell. Yeah, because you will need too much energy to remove those p electrons from the inner shell. So hence, okay, your s block elements tends to have oxidation states just limited to +1 or +2. Okay, like for example your sodium and magnesium. Now, so because this one, right, has a limitation, so this is a good comparison to your iron, which can exhibit 2 oxidation states as compared to 1 to sodium and 1 to magnesium. So it's just a comparison to showcase that feature here. Now, if you look at the table next, okay, whereby they showcase the various types of oxidation states that the elements can have. Interestingly, okay, scandium and zinc only have one each, right? And they have a fully filled 3D subshell for zinc 2 plus and an empty 3D subshell for scandium 3 plus. So that's why they are out of the transition element definition. Okay, so if you look at the middle 8, this is the variety of oxidation states they can have. That's a very interesting one. In fact, it kind of look like a pyramid here. Okay, so manganese has up to 7 oxidation states here. Okay, and then it starts to go down from iron onwards. Okay, so it goes up to from titanium we have 4 until manganese 7, and then after that when you go next to iron, it kind of like decrease in the range. Sorry, the range of oxidation states. So you can see there's a trend here. Okay, with the most oxidation state here for manganese. Okay, so from scandium to manganese, right? Okay, if you take their highest oxidation states, okay, you can see that all the 3d and 4s electrons has been used for bonding. Okay, and the reason is because of this part. Okay, for manganese, right? Okay, for it to exhibit a +7 oxidation states, right? All the electrons from the 4s and 3d subshell are all used up or used for bonding. Okay, as in this case it's covalent bonding, right? So hence you can reach oxidation state +7 in the form of manganate 7, MnO4 minus. Okay, and the next part is if you were to just take the maximum oxidation state from the other end, the other side, you can see that the numbers goes down. Okay, so how come the number will go down? It's because of this. Okay, so for iron, right? Okay, it has a 3d6 and 4s2. Okay, so for it to exhibit a +6 oxidation state, you are just using this 6. Okay, the 2 from 4s and the 4 from 3d. And you realize that the at 3d electrons here, they are not available for bonding. Okay, only the single ones can be used here. So this is the reason why the oxidation state, the maximum oxidation state from iron onwards, right, actually goes down because your number of unpaired 3d electrons is lesser. Okay, so here is a general way to see how to gauge the maximum number of oxidation states for each element. So the formula is the number of 4s electrons plus the number of unpaired 3d electrons. All right, we have arrived at one of my favorite tables here, okay, showcasing the oxidation states and compare it to the elements. Okay, and the formula that are in the table here showcase the oxidation state of that element in that formula, all right? So there's a lot of them, as you can see. Okay, and the ones highlighted in red are the ones you have seen so far throughout your chemistry learning. Right, let's see some of the how do they look like. Okay, so for manganese, right, I'm pretty sure you've seen the one in the middle. This manganate 7, potassium manganate, yeah, right, and it has a +7 oxidation state. This is manganate 6, +6 oxidation state, and it's dark green or green, right? And interesting fact is that manganate 7 is stabilized in acid, whereas manganate 6 is stabilized by alkali conditions, right? And MnO2 is the one that you have learned. Okay, it's one of the possible formula for the brown stains in your burette when you wash it out from manganate 7. Then for chromium, you have seen Cr3 plus already. You have seen this one also. Uh, do you? I think so. Okay, never mind. Okay, okay. This is the one that is unfortunately not in your chem lab. Yeah. So this is dichromate 6, which has a which has the orange colored what's that? Orange color, yeah. Okay, and this is chromate 6. ClO42 minus is chromate 6. Okay, chromate 6, dichromate 6. So both of them, their oxidation number is +6. Right, to take note this. Chromate 6 is the one without the it's just a single chromium, and dichromate 6 is the one with two chromiums here. And these are the interesting and rare ones that you may not have seen before. All right, so I'm going to showcase some of them. FeO42 minus, this purple solution. Okay, this is called ferrite 6. It's at the +6 oxidation state. Ferrite means iron, by the way. Iron's original name is called ferrium. Okay, ferrite 6. And this is actually a very strong oxidizing agent, apparently as strong as manganate 7. Okay, so that's for that. I want to showcase cobalt chloride. Cobalt chloride, okay, this solid, right, has its hydrated and anhydrous form in different colors. If I'm not wrong, blue is hydrated and pink, red, pink, this should be pink, is the anhydrous form. Last time when we have photography, right, the old film type, okay, the film has to be, or negative has to be kept in a desiccator with cobalt chloride, okay, to keep it. So when you see the crystals turn blue, that means the moisture has started to creep into the desiccator, right? Okay, then all you need to do is to just put this one into a hot pan and then heat it up, and then it will dry up to become the pink color one again, right? And that's how we reuse it as a desiccator or desiccating agent, right? This is the interesting bit, nickel tetracarbonyl, I think. Yeah, it's carbon monoxide as a ligand to nickel, right? And it looks like a yellowish kind of liquid here. Okay, and finally your the one that you're more familiar, copper 2 oxide and copper 1 oxide. Copper 2 oxide is this one, CuO, is the black solid that you get usually from thermal decomposition. Copper 1 oxide is the one that you learn as a brick red PBT in failings test. Right, when you add filling solution to a aliphatic aldehyde, then this is the brick PBT. All right, this slide is the recap of the points that we have just learned. Number one, okay, the number of available oxidation states for the elements increases from scandium to manganese, right? So the value of the max oxidation state suggests that all the available 3D and 4s electrons may have been used for bonding. Okay, in this case, is covalent bonding. And then for after manganese, with the most number of oxidation states, then it starts to decrease, right? From that to zinc, right? And it's due to the decrease in the number of electrons available for covalent bond formation. And when we are looking at the number of electrons, we are looking at the number of unpaired 3D electrons. Okay, we use that to form covalent bond, and from that, from manganese onwards, okay, it starts to decrease in the number of unpaired 3D electrons. I think I've just repeated myself. And finally, okay, the lower oxidation states tends to be found in ionic compounds. Like for example, the 2 plus charged ions. Okay, like iron 2 plus usually is found as a maybe like hydroxide in your QA, FeOH2. Whereas higher oxidation states tend to be found in compounds or ions that contains covalent bond, right? And that can include your oxides like titanium 4 oxide, and vanadium 5 oxide, and manganese 7 oxide. I hope I got it right. Okay, the more interesting one is the oxo anions, meaning oxygenated anions, oxygen bond or bound anions. Okay, like vanadate. This is called vanadate 5. This is chromate 6, dichromate 6, and manganate 7. And you actually need to know how to draw them. You need to know how to draw them. This is your Mn2O7. This one. This is your manganate 7. You need to know this quite well. So it's tetrahedral because there's only 4 bond pairs. Remember bond pairs, right? For double bonds and triple bonds is treated as one. There's one bond pair like that. Okay, so there are 4 bond pairs. This is your chromate 6. Yep, this one. And this is your dichromate 6. Alright, you need to know how to draw this, by the way. Okay, so do practice on this. Alright, another feature is that the oxidation states for each D block element can include +2, +3, or both. Alright, so for all the elements except scandium, all can exhibit +2 oxidation state, which means formally the element has lost 2 4s electrons. Okay, or another way is that to see the +3 oxidation state, okay, all the elements except zinc can exhibit +3 oxidation state, even though nickel, even though there's a nickel 3 plus, okay, it's not very important, okay, overall, not much use, by the way. Okay, and unlike the transition elements, scandium and zinc can only exhibit one oxidation state in the compound form. Alright, checkpoint 2. Okay, you may want to pause the video here to do this question on your own before you restart. Alright, okay, the answer, okay, we are looking at a titanium compound. Okay, the electronic configuration is given to you, right? And then which of the following compounds is unlikely to exist? Okay, so the trick to do this question is actually to check the oxidation state of titanium, right? Okay, the answer will be A because titanium, right? Okay, if you check its oxidation state, there's a +2, +3, and +3 here. Okay, and this titanium is +6. So can titanium reach up to +6? Okay, if you don't remember the trend of oxidation, so of maximum oxidation number, you can just use this, right? Okay, ultimately, if you lose all the electrons from the 4s and 3d, it should be max +4. Okay, so hence this is a very unlikely compound to exist, so that's the answer. Now we have arrived at the end of lecture 1, okay, but I still want to showcase what we are going to start off with for lecture 2, okay, which is on catalytic properties, right? So this will be the last slide for this video. Okay, now for catalytic property, okay, you need to understand the reason why or how transition elements can be effective catalysts in their various processes. And we need to start off the next video by understanding that catalysts are able to go by a different alternative reaction pathway because it's able to lower the activation energy. So if you were to use a energy profile diagram, this is an energy profile diagram, okay, where the reactants go through a reaction to form the products, then it has a go through a energy barrier. So that's called an activation energy. So catalyst has the ability to lower the activation energy so that the reaction can go faster, right? So use that to start off the next lecture video. Okay, and with that, I'll end this lecture video here. Okay, thank you.